Okay, welcome class, MEP 4C students. This is your opening video lesson for the trigonometry chapter. Chapter 1, we're looking at triangles. This should be a review for you. I'm going to go through some of the things you've looked at in grades 10 and 11. This worksheet, you have a copy of it already, is just a look at some of the key names of the triangle sides, as well as some of the key terms like similar triangles and corresponding angles. So just take note as I go through here, and then I'll explain the worksheet as you're to complete it on your own at home, and we'll follow up with a conclusion in class probably tomorrow or the next couple days. We'll wrap this up. So similar triangles, these are triangles that have the same shape but a different size. So I'm going to write those terms in here. Okay. You want some examples at the bottom of the page. You have two series of triangles. There's three nested triangles inside each series, and the labels are referred to on the worksheet. So you have triangle ABE, triangle ACF, and triangle ADG. These triangles you're going to be looking at, and you'll be measuring sides and some angles for, and then calculating some ratios on those. So the instructions are pretty clear there. The steps to follow on the front and the back page. You're to select a series of similar triangles, whether it be one or two. Those triangles within the series have, as I stated, the same shape but are different sizes. And you're going to be making some measurements in millimeters and then calculating some ratios to 3 decimal places for a chosen angle. All right. Now, some of the other properties of similar triangles you've looked at in the past. This exercise on this worksheet is a review, so I'm not going to fill in these next set of blanks here. We'll wrap that up when the worksheet is done. The other one here, by way of introduction, you should also know this already, so I'll fill this in. The sum of all angles in a triangle is equal to 180 degrees. That's a fact. The longest side in a triangle is called the hypotenuse, and that's always directly opposite the 90-degree angle, okay, which is also called a right angle. All right. Now, in a right triangle, this is a special type of triangle that has to have a 90-degree angle. We talk about these terms only with right triangles. There are three names that we use. Hypotenuse has been mentioned. The other two are opposite and adjacent. Now, these are not fixed sides, fixed locations. The opposite and adjacent are relative to the angle chosen. Okay, so it depends on which angle is chosen. So in each visual here, you have the star indicating the position of the angle. And here we have, for the first diagram, the opposite is directly across, and the adjacent is beside. The hypotenuse is, as expected, right across from the 90-degree angle. When we move the chosen angle to the top vertex, from the bottom vertex, the opposite is now the base of the triangle, and the adjacent is now the height. So again, those two terms, opposite and adjacent, they're relative. Hypotenuse is an absolute fixed location. All right, so when you go through your investigation, you need to know how to locate and label the opposite adjacent sides. Otherwise, it's pretty straightforward. Measure your side lengths, calculate your ratios, make sure you choose for your series. Let's say you choose series number 1, measure your angle A, and then the other top angle EFG. They're corresponding angles. They're going to be equal. Measure them in degrees, and then just indicate which corresponding angle was chosen. So if you decide, for example, you're going to go with series number 1, and you use the top angle here, then these angles at the top are all equal because of parallel lines. So the heights of each triangle are parallel, which makes the angles formed with the top side all equal. If you choose that angle, that's your chosen angle. That makes the base of the triangles the opposite side, and it makes the heights the adjacent. If, however, you choose the corner angle, don't choose the 90, but if you choose the corner angle A, then that's going to be a different situation. So each student in the class will choose their series, and then we're going to compare at the end for those that chose the other series. That's part of the worksheet on the back, is coming up with a conclusion based on these ratios, and also coming up with a conclusion for the other series of triangles and trying to think about some similarities and differences. Okay, so to try to finish that table, that's the expectation for tomorrow, and then we'll look at the conclusions here together as a class. Okay, before we get into trigonometry, review of trigonometry, we're just going to go briefly into Pythagorean Theorem, and this exercise will review the ratios, which eventually will connect again to sine, cosine, and tangent. But before we do that, we're going to look at rate conversion. A rate conversion is going to be necessary when we're dealing with metric or imperial units. So there might be a label on the triangle, or the side length might be in metric and another side length is in imperial, and we have to convert so that we can use a common unit. I've used this method before, and it might be new to you, so I'll go through this example together. First, you'll see a table at the top of this slide. This shows some of the common metric units: millimeters, centimeters, meters, kilometers. And it also gives some equivalences here. So 1 centimeter is equal to 10 millimeters, 1 kilometer is equal to 1,000 meters. On the imperial side, we have some common equivalences. A yard is 3 feet, a foot is 12 inches, a mile is almost 1,800 yards. Those are the equivalences. There's also a crossover in the table which goes from the given unit here, one of whatever, meters, for example, over to yards. You can cross over and see that a meter is a little bit more than 1 yard. Okay, so that's another example of an equivalence that can be useful when making conversions. And you have the same thing over here if you're trying to convert, for example, a mile into kilometers. Quite often I just memorize it as 1.6, but you can see the equivalence is given to 4 decimal places: 1.6093 kilometers for every 1 mile. That allows us to write what's called a rate. And so in this method, you need to be able to find these equivalences, which are from the table, or you look them up, or maybe you've memorized them. You need to be able to take the equivalence, write it down, and write down the rates that are associated with that, and then you apply proportional reasoning using that rate. So here's an example here where we're trying to convert, say, 15 feet into yards. So we know that 1 yard is equal to 3 feet. That's a fact. We can from that state that, well, there's 1 yard for every 3 feet, or we could state that as there's 3 feet for every 1 yard. So those rates are written down with the expectation that one of them is going to be used. The appropriate rate that we select, I'll underline here, the appropriate rate. This is where you can make a mistake. This method is pretty much foolproof. It'll use multiplication. We will always be multiplying. So you'll never have to worry about, do I multiply or do I divide? You will always multiply. The given quantity, what's the given quantity? Well, the given quantity is what we start with. It's 15 feet. Multiply it by the appropriate rate in order to produce the desired quantity. What's the desired quantity? Well, it's the number, but it's also the desired unit, which is yards. Okay, so we're trying to go into yards from feet. So the rate that we're going to choose is going to be that which eliminates feet as a unit and introduces yard as a unit. And so with fractions, it's a lot like this with units as well. You multiply across the top and you multiply across the bottom. You can approach it that way. So numerically the answer is 15 times 1 over 1 times 3. Okay, which is of course 15 divided by 3, which is 5. With the units, we see that feet disappears. Feet will cancel out, almost as if we can cancel out 3 and 15 and replace it or simplify it to 5 over 1. We do the same thing with the units. So in this method, it's always multiplication. We use the appropriate rate, and we should end up with the desired rate, the desired unit rather. All right, so this is rate conversion. We can use this method for other conversions that are not immediately obvious from the table. So let's look at, say, for example, we wanted to know how many centimeters are in a foot. Okay, well, we have centimeters to inches here in our table. We have centimeters to inches there. We have inches back to centimeters, but we don't have a conversion or an equivalence that gives us centimeters equals so many feet. We'd actually have to cross over first from centimeters to inches and then from inches to feet. So I'll model this example here using the same approach. The first step is find the equivalence of the units being related. In this case, there's actually 3 units, so I'm going to write them down. We know that 1 foot is equal to 12 inches. We know that 1 inch is equal to 2.54 centimeters. Try to be as exact as you can. If you know what the 2 decimal places, write it down. If you want to estimate, but or approximate, but understand that approximation always introduces error. And for large amounts, the error gets bigger. Okay. All right, so these are our 2 equivalences. And let's write for each of those the rates that are possible. Okay, so this is usually pretty straightforward. You're going to write it as a fraction. That's what a rate is with a unit. So we can say that there's 1 foot for every 12 inches. Or we can say that there's 12 inches for every 1 foot. Both rates express the same information. For the second equivalence, we could say that there is 1 inch for every 2.54 centimeters. Or we could say that, well, there is 2.54 centimeters in an inch. So we can say for every 1 inch. Okay, so those are our rates. Now, let's start out with the given quantity is, all right, we make it up. So let's say we're trying to go from centimeters to feet. And the given is 123 centimeters. Okay, so I'm just choosing that amount, just make it up, something that has meaning to us. Okay, so what is 123 centimeters? More than a meter. How many feet is that? Well, you're going to estimate. We know that a meter is a little bit more than a yard, and a yard is 3 feet. So just use your estimation skills and say that 123 centimeters is probably something around maybe close to 4 feet. Okay, so let's just go with that as our estimate. Keep that in mind and see how our actual calculation compares. Okay. All right, so how do we start off? Well, let's use the rates that we've written down. Let's use the given quantity, and let's realize that we're trying to go to the desired unit, which is feet. So let's start out by writing down 123 centimeters. Let's then apply a couple multiplications of rates. Remember, we're always multiplying here. And the 2 rates that we're going to use are going to allow us to go into our final unit, which is going to be feet. So let's write that down. On the other side of the equal sign, we want to go to feet. Okay, so let's get rid of centimeters. How do we do that? Let's use a rate that eliminates centimeters by cancellation. So let's put centimeters in the denominator of the rate, which makes sense because if you really wanted to convert centimeters to inches, you would divide by 2.54, knowing that every inch takes 2.54 centimeters from your total length. So that's going to get us from centimeters to inches. Now, to go from inches to feet, we have to realize that there are 12 inches in a foot, so whatever the amount is that we get from this calculation, we would have to divide that by 12. So, all right, when we're using multiplication, it's going to appear as 1 foot for every 12 inches, which is going to give the same mathematical result. Okay, so canceling out our units, centimeters cancels with centimeters, inches cancels with inches, and lo and behold, we're left with our desired unit, which is feet. Okay, we know that. But what is the desired quantity? Okay, well, so the math here takes over. We're finished with the units. 123 times 1 times 1 is what we have in the numerator. I'm going to write 123 as 123 over 1, just to help you see that all 3 of these numbers are fractions. And you know how to multiply fractions. You multiply across the top, you multiply across the bottom, and then you simplify if necessary. So we could approach it like that. Would be one way. 123 times 1 times 1, all over 2.54 times 12. Alternatively, you could just, on your calculator, go 123 divided by 2.54 times 12, or you could enter in 123 divided by 2.54, press equals, and then take that result, whatever that is, and then divide that by 12, and that'll give you your answer as well. Okay, so we have to work this out, so get a calculator and we'll fill that in, and then we're done. Okay, my final answer that I get after doing these two divisions is 4.04. I'll round it to 2 decimal places. So 4.04 is the number of feet that corresponds to 123 centimeters. They're equal. Okay, and it was close to our estimate, given the fact that a meter is a little bit more than a yard, and we have more than a meter. So it's good to have an estimation before you start your calculation, just so you can make sense of the answer, just in case, you know, we goof on our calculation, we get 40.4, and you think, oh, that 40.4, I got an answer, I'll write that down. Okay, but it doesn't match with the estimate, so it's always good to go back and just see if, in fact, how close we were, and yes, we're pretty close. Okay, good. So that is how we use the rate conversion method. Apply that method. It's very consistent. You're going to do the same thing every time. So just study these steps, and if you have any questions, see me tomorrow. And I'd like to see you trying that method as well in your work. Okay, it takes a little bit of extra writing, but I really want to emphasize communication in your work. So give it a shot and give me some feedback on how it worked out tomorrow. All right, the last thing I want to look at as far as a review, you're independently looking at your ratios and right triangles for similar right triangles. Now I want to just go and make sure that you're also familiar with the other key property of triangles, is that side lengths can be calculated using a special formula which most students know as the Pythagorean Theorem. Okay, it's pretty easy to use the formula. There's some times where you have to be careful depending on which side you're solving for. But so let's first of all, again, make sure we know that this is only applicable in a right triangle. Different triangles that are not right do not have a hypotenuse, so we can't always say that the longest side of any triangle is the hypotenuse, but in a right triangle it is. And this is what the Pythagorean theorem states. Now I'm going to show you the whole slide here, because most students just say, oh, Pythagorean theorem, c squared equals a squared plus b squared, and I'm just going to use it. Okay, the problem with that is sometimes the hypotenuse is not labeled C, and if you're so locked into your labeling, you're going to make a lot of mistakes, and it's going to be frustrating, and you're not really going to be learning much. So try to look at the definition and see how it matches your formula that you've learned before. It says in a right triangle, the square, which means multiplying it by itself using an exponent of 2, the square of what? The length of the hypotenuse, so that would be C, is equal to the sum, which means that there's going to be addition, the sum of two other squares. One is the base times itself, and the other one is the height times itself. And it's interesting visually, what this actually means is that if you make a square off the hypotenuse side, that area of that square, which is C times C, okay, because that side length would also be C, is going to be equal in total to the area of A times A and B times B. And maybe for some of you that might be new. That is a visual interpretation of the Pythagorean theorem. Is it's just really big square is made up of two little squares when you use the sides of a right triangle. Okay, so hypotenuse squared equals base squared plus height squared is what I prefer to use. And of course, whenever we have our triangle labeled, if it's conveniently labeled ABC, like so, where C is right at the 90-degree angle. Doesn't really matter where the A and the B are, because we're going to reverse the order of the adding, and that will still give us the same result. If we call one the base or the other the height, it kind of just depends on actually which way you look at the triangle, but the hypotenuse is always going to be there. Then as long as the labeling is consistent with our formula, you can use c squared equals a squared plus b squared. Okay? All right, so that's a review of the Pythagorean theorem. And from there, let's just maybe look at one example which actually comes right out of your textbook practice question number 3A on page 3. The question says determine Q, which is the hypotenuse of the triangle. There's a little bit of conversion that needs to be done because the side lengths are in millimeters and meters, which are both metric units, but they're not both common to each other. Okay, so we're going to have to convert probably millimeters into meters. I'm going to add a little bit extra challenge, which is going to allow you to see that okay, the ratios of sides for that angle that we choose is going to be a review item as well. Okay, so the first thing I'm going to do is label my triangle. I'm going to label it ABC, but you know what this time? I'm going to label it so that I put B on the 90-degree angle, A over here, and C over here. Now, for some of you, if you remember in labeling triangles, you may recall that the lowercase letter is quite often used opposite the capital letter. So this question says determine Q. I'm going to actually determine little b. Okay, so just make the adjustment here. Okay, so determine Q or b. In this case, it's the hypotenuse. So the formula that I would write would actually be b squared equals a squared plus c squared. Okay, and that's consistent with hypotenuse squared equals, in this case, base squared plus height squared. And as I just mentioned at the start, you know, if you're watching this video and some of this stuff is you know, going over your head, or if I'm talking faster than you're able to take in the information, rewind. Just go back and look at a previous clip. On the other hand, if it's really familiar to you and you're not learning much from this, skip ahead to the very end where I wrap up what I'm expecting you to do tomorrow from this slide, and then you're done. And come in tomorrow having looked at the information at least, because I'll usually be giving you a quiz on the content from the previous lesson. Okay, so here we are with this formula. We've done everything we need to as far as labeling of the triangle, except we haven't converted our units. So here I'm going to go with conversion to meters. So I'm going to go from millimeters rather to meters. Now they're both lowercase m, so you have to be careful how you write the units. For the metric, it's a little bit more. The units look the same. You know, often it's just the prefix centi, kilo, milli. Now, let's start with the desired unit is meters. The given unit and quantity are millimeters, 223 of them, and we need to know what the equivalence is. So in this case, we know that 1 meter is 100 centimeters. Okay, so think of a meter stick. We know that 1 centimeter is 10 millimeters. So from that, we could actually say that 1 meter is equal to 1,000 millimeters. Now that's just using proportional reasoning. I'm not actually applying a rate conversion method process there, but you know, you could take it at the extreme and say, okay, well, 1 meter times you know, 10 centimeters for every 1 meter, and there are, sorry, rather 100 centimeters for 1 meter, and there are 10 millimeters for every 1 centimeter, and then we could cancel our units, and we would see that centimeters goes and meters goes, and we end up with, oops, we end up with 10,000, or sorry, 1,000, 100 times 10. So this is our equivalence. Okay, so we can use from that we can write down the rates. Okay, so this is our equivalence here, and then the rate that would go with that, right beside it, would be again 1 meter for every 1,000 millimeters, or we can write 1,000 millimeters for every 1 meter. So that's what I'm going to do. I'm going to multiply by the desired rate, or the appropriate rate in this case, which is going to eliminate millimeters. So I'm going to take the rate that has meters in the numerator and millimeters in the denominator. So really, for this, I'm just dividing by 1,000. Okay. Which, again, a lot of you would say that's a no-brainer. That's what I would have done. This is too complicated. But I want to see the units with your calculation. Okay. And some of you're going to have struggle with showing your work. Okay, that's why I'm modeling here for you, writing the equivalence, writing the rate, set up your given unit and quantity, multiply by the appropriate rate, and then do the math. Okay, so 223 divided by 1,000 is going to be 0.223 meters. Okay, so now I can update my diagram up here and say that this is the same as 0.223 meters. All right, we've arrived at the result here of converting the unit. Again, I want to remind you that on the video lessons, I'm modeling how I want you to approach a certain task or to do a certain calculation. It might take me 5 minutes to explain this the first time, and then after that, you get the hang of it. Again, keep in mind you can fast forward through the video if you're having a hard time with the content. You can go back. All right. All right, let's return to the task at hand, which was to determine the value of the hypotenuse. So in this case, I now have both of my lengths in a common unit, which is meters. I can now use the Pythagorean Theorem, just directly remembering that the Pythagorean Theorem says hypotenuse squared equals base squared plus height squared. And the base is little a, which is directly opposite from vertex A. So it's going to be base squared plus height squared, and now I fill in my values. So the square of b is equal to 0.45 times 0.45 plus 0.223 times 0.223. So I'll just pause now. And what I would encourage you to do in the videos is pause, do a calculation yourself, and don't just passively sit and listen to me. Make sure that you can reproduce the same result, and if you're able to, then that confirms that you're doing it correctly. All right, you're going to see the full solution. I sometimes do this in my videos where I give you time to work it out, and then you can come back and see how I wrote it down, and also the calculated value. So I encourage you to show your steps, write the formula initially, make the substitution, calculate the individual values. Notice that I didn't just load it all in and write down the final answer when I added the squares of the base and the height. I summed them up after the individual values were calculated. Keep in mind that's not equal to the hypotenuse, but it's equal to the square of the hypotenuse. So here's where you have to use opposite operations. So the squared operation means something times itself. So b times b is what b squared means. So if you want to calculate the value of the hypotenuse, little b, then you have to take the square root of that value, 0.252229, and I'm giving that as 0.50, rounding that to the fewest number of decimal places from the initial values. So what does that mean? Well, 0.45 had 2 decimal places and 0.223 had 3. So I would just go with the fewest number just to try to match the precision in the original values. So 0.45 is not as precise as 0.223. So we should try to reflect that in our final answer. And keep in mind, this actually has some meaning. It's so many meters. So we can't just use as many decimal places as we want. I can talk about that more with some of you if you're wondering what I mean by precision, and it has a little bit to do with instruments that you might use to measure those lengths. Okay, just also look for reasonableness of the answer. Keep in mind the hypotenuse is the longest side of the triangle, so it has to be more than 45 centimeters or 0.45 meters. So we couldn't have gotten a value of less than 0.45. 0.5 is pretty reasonable given that the base of the triangle was longer than the height, and you have to be careful with the diagram. It doesn't always look that way, so just trust the numbers. The last part of this question, which I tagged on to what your textbook required of you, was to choose a vertex and state the three ratios for that angle. So this sort of ties in with what you're doing on your worksheet. All right, so I'm going to choose a vertex, and I'm going to use the top. Okay, so I'm going to use vertex A as my chosen vertex, and I'll complete this in blue. Okay, so vertex A. So that means my chosen angle is angle A, and then relative to that, we would have opposite would be little a. The adjacent would be little c, and the hypotenuse would be, as expected, little b. Okay, so the three possible ratios are the opposite over the hypotenuse. That's called the sine ratio. You may remember that from grade 11. So the opposite over hypotenuse would be 0.45 divided by 0.50. Okay, you can just leave it as a fraction. You don't have to simplify that. If you do, you'd get 0.9. Okay, so the opposite is about 90% of the hypotenuse. The other ratio is the adjacent over the hypotenuse, and you may remember that as cosine. That's the AH of SOHCAHTOA. Sine is the OH, and that would be 0.223 divided by 0.5. 0. Keep in mind again, if you actually calculate the value, you're going to get 0.446. So the height of the triangle is less than half of the hypotenuse, about 45% of it. Okay, that's what 0.446 is as a percentage. And finally, the OA of SOHCAHTOA, starting to tie this in with where we're going to go next, is the opposite over adjacent, and that ratio is called the tangent ratio. Opposite over adjacent is 0.45 over 0.223. Now in this case, in right triangle, the opposite and the adjacent always have to be less than the hypotenuse, but one can be larger than the other, or they can be equal in a isosceles triangle or maybe an equilateral triangle. Reason why I mention that is because the opposite over adjacent ratio quite often for angles more than 45 degrees can be more than 1. And if we were to calculate the value of 0.45 over 0.223, we get 2.0, okay, approximately. You notice I put a dot above the equal sign when I've rounded, and that means I've approximated, okay? So you try to do that as well. If it's exactly equal, write equal sign. If not, put a dot over the equal sign, please. So 2, meaning that the opposite side of the triangle is, from angle A anyway, about twice as long as the adjacent, and that's consistent with these numbers. Again, don't let the diagram deceive you, but 0.45 is pretty much exactly double 0.223. Okay, so that's what the ratios mean, and we can talk about that more tomorrow, but those would be the 3 unique ratios that are possible for angle A, and if you choose a different angle, you'd get different ratios. Okay, so see you tomorrow, and I hope you come in with some questions and be prepared for a short little quiz. The other questions from your Activate Prior Knowledge on pages 2 and 3 are good practice as well, and we can continue to work on those in class. So work on the completion of the table, please, and come in tomorrow prepared to discuss your results. Thanks.